And we're back to finish up the examples for 15.2. So here we are in example 5. We are asked to set up integrals but not evaluate. I am going to go ahead and evaluate these because as important as I think the setup is, I also feel that being able to follow the problem through to completion is equally important. So let's start with this. Part A, we're given that we want to find the volume under the surface. Right away, I'm going to stop. That means that z equals 1 plus x squared y squared. That is our integrand. And above the region enclosed by x equals y squared and x equals 4. So that is our region D. That's our region of integration. So we need to draw that. If I draw that x equals y squared is a sideways parabola, and just draw a few of these tick marks on here. It has points that go through the origin, 1, 1, 1, negative 1, 2, 4, and negative 2, 4. And then we can draw that nice parabolic shape that we all know. So that's one of the equations. This is x equals y squared. And then we're also told that x is equal to 4, which is a vertical line going through 4. Okay, so looking at this, I can see what is being bound here is between that vertical line and the sideways parabola. So that's going to be my region D that I need to integrate over. We need to figure out if we should use type 1 or type 2. I'm looking at this, and as strange as it seems, it looks like we could do a type 2 where the parabola is on the left and the vertical line is on the right. And then y would go from -2 to 2. So I'm going to go ahead and do that. I'm going to use a type 2 region. And so we'll have y squared on the left of x and 4 on the right. And while that's happening, y is going between -2 and 2. So if we want to calculate the volume, we can use these bounds. We have volume is equal to the integral from -2 to 2, the integral from y squared to 4 of the integrand, which is 1 plus x squared y squared. And then we're looking at dx dy when we solve this. All right, so if we integrate with respect to x first, that's going to give us the integral from -2 to 2 of x plus 1/3, and I'm going to write the y squared first and the x cubed second. We're going to evaluate from y squared up to 4. After we do that evaluation, we'll be able to integrate with respect to dy. Okay, going on. This is going to equal the integral from -2 to 2. Now I evaluate at 4. I get 4 plus 1/3 y squared x cubed, 4 cubed, I'll write that over 3 y squared. Okay, so that's my first evaluation. Now I evaluate at y squared, and that's going to give me, everywhere there's an x, put in a y squared, so I get y squared plus 1/3 y squared times y squared. And then evaluate with respect to dy. Now I need to distribute and combine like terms. So this gives me the integral from -2 to 2 of 4 plus 64 over 3 y squared minus y squared minus 1/3 y to the 4th. I can combine the like terms of the 64/3 y squared and the minus y squared by writing that minus y squared is 3 over 3. Then I'll get that this is the integral from -2 to 2 of 4 plus 61 over 3 y squared minus 1/3 y to the 4th. Okay, now we can go ahead and integrate one final time. We get 4y plus 61 over 9 y cubed minus 1 over 15 y to the 5th. This will get evaluated from -2 to 2. At this point, a lot of people like to try to use symmetry, and it's fine if you do it right. I tend not to use symmetry when I'm evaluating over symmetric bounds, just because I'd rather get it right than get it fast. So I'm going to go ahead and evaluate it 2 and then subtract the evaluation at -2. So this is equal to 4 times 2 is 8 plus 61 times 8 over 9 minus 1 over, well, actually the 2 to the 5th is going to be 32 over 15 minus, in parentheses, 4 times -2 is -8 plus, that'll be minus actually, because a -2 cubed gives me a minus, so I get 61 times 8 over 9. And then the y to the 5th also gives me a minus, so I'll get a double negative plus 32 over 15. Okay, distribute and combine like terms. We have 8 plus 8, that will be 16. We have 2 of those 61 times 8 over 9s, so that will be plus 61 times 8 times 2, because there's 2 of them, over 9. And we have 2 of those negative 32 over 15, so it'll be minus 64 over 15. I can pull out my calculator to figure out what this is. That 61 times 8 times 2 is just 976 divided by 9 plus 16 minus 64 divided by 15. And that gives me a really big number. And that's going to give me approximately 5,408 over 45. Okay, so I'm noticing the number I got at the end is not what I expected, because I did work this out earlier. So that was kind of an alarm to me that something went wrong. And so what went wrong was when I was evaluating at y squared and plugging it into x cubed, I did not cube it. So there should have been a cube there. That would mean that y squared cubed means y to the 6th times a y squared. That would mean that over here I have y to the 8th. And let's see if that is the only thing. So let's see. Yeah, that should be good. Yeah, I think we're good from there. Okay, so now I want to fix what's wrong in here. First, I'm going to get rid of that because that's wrong. Other stuff I can just go through and very carefully fix what's wrong. So the 4, the 64 over 3y squared is good. The minus y squared is good. The minus 1/3 y to the 8th is good now, so I'll go ahead and fix that here. Y to the 8th. Okay, so it's just that last term that needs to be fixed. All right, so that'll give me 1/9 y to the 9th, or multiplying that by 1/3 gives me 1 over 27 y to the 9th. Okay, that's a little bit better. All right, let's see what we get now. Sorry about that. So I'm going to evaluate it 2. That gives me 4 times 2 is 8 plus 61 times 8 over 9 minus 1 over 27. And actually that won't be a 1 because it is 2 raised to the 9th power, which is 512. Okay, minus, now I'm going to evaluate at -2. So that'll be 4 times -2 is -8. Y cubed with the negative, it'll be negative again. So minus 61 times 8 over 9. Minus, and then I'll have a double negative because the -2 to the 9th will be negative. So it'll be plus, and that'll be 512 over 27. Okay, that's a little bit better. I should figure out what 61 times 8 is. It's 488. And then times 2 will be 976. Okay, just getting some numbers here. Combining my like terms and fractions, I have 8 plus 8 is 16. I have 2 of the 61 times 8 over 9s, and that will end up giving me plus 976 over 9. And then I have 2 of the negative 5/12s over 27, and that will give me a negative 1024 over 27. Okay, now I'll go ahead and get out my calculator. 16 plus 976 divided by 9 minus 1024 divided by 27. That gives me a grand total of 2,336 over 27. That's approximately 86.519 or so, okay? So that's the amount of volume under that surface and above the region that has been described. Okay, the next one. All right, this one is really interesting because the region of integration is not obvious. And we like it to be obvious, but it's not. Okay, so they're telling us that we have to find the volume and of a region that is bounded by the following planes: z equals x, y equals x, x plus y equals 2, and z equals 0. Okay, so z equals 0 is the xy plane. Z equals x is my integrand. Okay, it's also a slanted plane that runs parallel to the y-axis. So I know that if we think of the region that we're integrating over, the floor is the xy plane and the ceiling is z equals x. Now the y equals x and x plus y equals 2, that's going to be our region of integration. And we'll see how that's not necessarily clear enough. So let's go ahead and draw that. I have an xy axis. And if I draw the line y equals x on here, I get this line. And then I'm going to put in the line x plus y equals 2. That one has intercepts at 0, 2, and 2, 0. So I can go ahead and draw that line. So this is x plus y equals 2, and the other one is y equals x. Okay, I have two possible regions of integration, but honestly, like I'm just going to put dots where they could be. Okay, those are the two regions, but notice that actually neither of them is a closed off region. When we are looking at a region of integration, it needs to be closed and bounded. Like there needs to be a function covering all the sides of the region. We have nowhere in here that the x-axis or the y-axis is closed off. So we might need to actually kind of look at a picture of this. So what I've done is I've brought in CalcPlot 3D so that we can look at this. And on here, it's a three-dimensional grapher. And so I've had to turn it to kind of give us a bit of a 2D view where we can see the plane y equals x, and then the plane x plus y equals 2. Now, we can see on here very clearly now that like there are no closed up regions, right? Everything's open. But we are wondering if things are, closed off by the x-axis or the y-axis. So what I'm going to do is bring in the function z equals x and see if it helps us. Okay, so there's z equals x, and I need to get myself a good view here. Okay. It doesn't really seem like a good view, does it? Okay, so the blue and the green planes, those are from the region of integration. The z equals x, that's that orangish beigeish plane. It looks like it's going through the y-axis. And if I flip this over a little bit, this is actually our closed off region where I see pink and yellow and blue. That's where the z-axis is cutting through the y-axis. Sorry, the z equals x plane is cutting through the y-axis. And here's what else I can do. I can add in the plane z equals 0. And what we're going to see is we're going to get a closed up triangular box. So I do that. Whoop, there it is. Purple gave us a floor. Now, our region of integration is the region that is closed off by all the intersections of these planes. Okay, I'm hoping that makes it a little bit clearer and that didn't just mystify anybody. But getting back to what we've got, another way to see this without using technology is to actually just draw for yourself a quick little XYZ octant and then put in the plane z equals x. So z equals x we know has to be parallel to the y-axis, and so it would be crossing through that y-axis, which means that the winner is the orange dot. So I can get rid of the blue dot because z equals 0 is going to give us that closure. Not z equals 0. Z equals x is going to give us that closure. Okay, that was a lot of work and talking through to figure out just which of the triangles was actually going to be our region of integration. Now we can set things up. So I'm looking at this, and if I wanted to do a type 2 region, I would have one left and two rights. So I don't want to do a type 2 region. I want to do a type 1 region. And with a type 1, I see a bottom, that's the y equals x, and the top, that's the y equals 2 minus x. So I'm going to use that. So the lower bound for y is x, and the upper bound for y is 2 minus x. And in that time, it looks like x is going from 0 up to 1. So then we can set up our volume integral. We have the integral from 0 to 1, that's for x, and the integral from x to 2 minus x, that's for y. Our integrand is the z equals x, so that's that plane that is up above, it's our surface. So we're going to put in x, and then dy dx. So we'll go ahead and work through this. If I find the antiderivative with respect to y, this gives me the integral from 0 to 1 of xy from x to 2 minus x dx. I'll evaluate that at those bounds. So this is the integral from 0 to 1 of x times. Now I'm going to look at y evaluated at 2 minus x minus the evaluation at x dx. Combine like terms and distribute. The integral from 0 to 1 of 2x minus 2x squared dx. Okay, go ahead and integrate with respect to x. We get this is equal to x squared minus 2/3 x cubed from 0 to 1. That gives me 1 minus 2/3 minus 0, which is 1/3. And that is the value of the volume of the region that's bounded by those planes. Okay, next problem. Here we are asked to sketch the region of integration and then change the order of integration. So that's going to be a very useful skill to have. So right now, what I'm seeing is the way this is written, I see dx is in the inner integral. So I have 1/2 y is less than or equal to x is less than or equal to 1. That means we have the equations x equals 1/2 y and x equals 1 showing up. My y bounds are 0 to 2. So let's see what that looks like on a graph. Okay, get in 1 and 2, 1 and 2. Okay, so the line, let's see, the line x equals 1/2 y can also be rewritten as y equals 2x. And that will go through the origin. When x is 1, y will be 2. And I can connect my dots after that. So this is y equals 2x. X equals 1 is the vertical line going through 1. And then y equals 0, that's going to be the horizontal line through the x-axis. And y equals 2 is that intersection point where the vertical line and the slanted line cross. So we have our region of integration here now. That's our D. And so with the way everything's written, I want to rewrite this as, okay, what was this before? This was a type 2. We're going to rewrite as type 1. So now we're looking at bounds for y. Okay, the lower bound for y, it looks like it's still 0. But the upper bound for y is now that slanted line, the y equals 2x. And while that's happening, the lower bound for x is 0, and the upper bound is 1. So I can rewrite this now. So here's what's true. The integral from 0 to 2, the integral from y halves to 1 of y cosine of x cubed minus 1 dx dy is equal to the integral from 0 to 1, the integral from 0 to 2x of y cosine of x cubed minus 1 dy dx. Now I want you to notice something. The way it was written the first way, I would have had to integrate with respect to x first. And I don't know how to integrate cosine of x cubed minus 1. I don't think you actually can. It would be nice if I could do a u substitution on it, but the du isn't in there, so nothing's really going to work. So by switching the order of integration, what I want you to see now is that I can actually integrate this. And that's the valuable tool that you're learning here. So if I'm integrating with respect to y first, then I'm not worried about the cosine of x cubed minus 1. I'm just worried about the y. So we're going to focus in on that. Okay, so integrating with respect to y, I get the integral from 0 to 1 of 1/2 y squared cosine of x cubed minus 1 evaluated from 0 to 2x, and then a dx after I do my evaluation. Evaluating at 2x, I get the integral from 0 to 1 of 1/2 times 2x all squared cosine of x cubed minus 1 minus 0, because that y squared would be 0 squared and the whole thing will go to 0. So I don't have anything more here. Now I'm just going to rewrite this one more. Squaring my 2x gives me 4x squared divided by 2 is going to be the integral from 0 to 1 of 2x squared cosine of x cubed minus 1 dx. This I can integrate. So what I need to notice is that I could do a u sub. And in my u sub, I'm going to take care of that ugly part, the x cubed minus 1. We'll let u be the x cubed minus 1. Then du is 3x squared dx, which I don't have a 3x squared dx. I have a 2x squared dx. Well, I can divide out the 3. I get 1/3 du is equal to x squared dx. And then I can multiply both sides by a 2, which means that 2/3 du will replace 2x squared dx. Okay, so and then in a u sub, I would be looking at the integral of 2/3 cosine of u du. That I can handle. The antiderivative of cosine is sine. So this just gives me 2/3 sine of u. Going back to my problem, I replace the u, This gives me, let's see, 2/3 sine of x cubed minus 1, evaluated from 0 to 1. Evaluating at 1 gives me 2/3 sine of 0, because 1 minus 1 is 0, minus sine of negative 1. Sine of 0 is 0, so this is just negative 2/3 sine of negative 1, which is good enough. We're done at this point. However, this is equal to negative 2/3 times negative sine of positive 1, which ends up being positive 2/3 sine of 1. And here's an explanation for that. Sine is an odd function. So sine of a negative angle is equal to negative sine of the angle. And that just allows us to handle that sine of a negative 1. Either answer is correct, though. It doesn't matter which one you end up using. All right, that concludes the section 15.2. If you do have any questions at all, please reach out.